Okay, welcome students. Let's cover section 7.1, eigenvalues and eigenvectors. Seven point one. The eigenvalues and eigenvectors. The definition let A be an m by n matrix. And any value of lambda, that's the Greek letter lambda, for which A times vector V is equal to lambda times vector V, has non-trivial solutions V are called eigenvalues of A. This corresponding non-zero vectors V called eigenvectors of A. With eigenvalues and eigenvectors. Each eigenvalue has a corresponding eigenvector. One, given that V1 is equal to negative 1, 1, and V2 is equal to 5, 6, are the eigenvectors of A, and A is equal to negative 2, 5, 6, and negative 1, and determine the eigenvectors of A, or sorry, the eigenvalues of A. Oh, okay, so let's look at the equation we're working with. So AV1 is equal to lambda V1. Right? A times V1 is equal to lambda times V1. And lambda is just a scalar. V1 is a vector. And A is a matrix. So let's set this up. A is negative 2, 5, 6, negative 1. V1 is negative 1, 1. And that's going to equal lambda times negative 1, 1. Okay. Okay. Okay, so let's multiply this out and see what we get. We're gonna get negative 2 times negative 1, which is 2, plus 5 times 1, which is 5, equals negative lambda. Okay. And then 6 times negative 1, 6, plus negative 1 times 1 is negative 1 is equal to lambda. Okay, and so this is going to be 7 is equal to lambda, or sorry, negative lambda, and negative 7 is equal to lambda. So lambda is negative 7. Okay. So lambda 1, I should say, lambda sub 1 is equal to negative 7. So that's my first eigenvalue. So let's try the next one here. A times V2 is equal to lambda times V2. This is going to become negative 2, 5, 6, negative 1 times V2, which was 5, 6. Is equal to lambda times 5, 6. Okay, so this is going to be negative 2 times 5 is negative 10, plus 30 is equal to 5 times lambda. Okay, and then 30 plus negative 6 is equal to 6 times lambda. So this is going to become 20 is equal to 5 times lambda, and 24 is equal to 6 times lambda. So obviously lambda has to be equal to 4. So that's lambda 2 is equal to 4. Okay. Now we were given the eigenvectors, but could we find the eigenvectors and the eigenvalues if we were just given the matrix A? Okay, because these eigenvalues and eigenvectors, they're very special, and and each unique matrix produces unique eigenvalues and eigenvectors. So what if we were just given matrix A? Oh, and this is n by n. I'm sorry. Go ahead and fix it. And then it has to be a square matrix. Okay, so if we have just AV is equal to lambda V, okay, then if I take and I subtract lambda V from both sides, AV minus lambda V is equal to 0. And so, what I get is I get A minus lambda, okay, times vector V is equal to 0. Now, I have a problem in that A is a matrix and lambda is a scalar. So I can't combine a matrix and a scalar by subtracting. So what I'm going to do is something kind of sneaky. I'm going to multiply lambda by the identity in. Okay, we multiply by in, and that will turn those scalar values into an identity matrix that just has lambdas along the diagonals and zeros everywhere else. Okay, and so then I could subtract A minus lambda. Okay, and solve for V. Okay, we first probably solve for lambda and then solve for V. So let me show you how this works. Okay, so we use matrix subtraction since lambda IV is equal to lambda V. Okay. Okay, so we multiply it by I. Okay, but this n by n linear system okay, has non-trivial solutions okay, meaning lambda isn't 0. Which are the eigenvectors if and only if, okay, the determinant of A minus lambda I is equal to 0. Okay, if and only if the determinant of that is equal to 0. That is a solution only exists if and only if AI, A minus lambda I is linearly independent otherwise A would be equal to the 0 vector or V would be equal to the 0 vector, and that's a trivial solution. Okay, so what we're going to do is we're going to say that this thing has a solution only when we have A minus lambda I, or yeah, lambda I, times V naught is equal to 0. And that's going to have a linearly independent. That's going to be linearly independent if and only if the determinant of A minus lambda I is equal to 0. For this guy, the solution exists if and only if the determinant of A minus lambda I is equal to 0. So that determinant is equal to 0, then A minus lambda I is linearly independent. Okay, definition. Okay, for a given n by n matrix A, the polynomial P of lambda defined by P of lambda is equal to the determinant of A minus lambda I is called the characteristic polynomial of A, and the equation P of lambda equaling 0 is called the characteristic equation of A. Okay. Okay, so let's take example 1, but now let's do example 1 without being given the eigenvectors. Let's see if we can come up with the eigenvectors and the eigenvalues all by ourselves. Okay. Okay. So find all eigenvalues and eigenvectors given matrix A equals -2, 5, 6, and -1. Okay, so let's do this. Okay, so what are we gonna do? We're gonna find the determinant. We're gonna find when is the determinant of A minus lambda I equal to 0. Okay. So what are we gonna do? We're gonna go -2, 5, 6, -1 minus lambda times I. So this is I2 because it's a 2 by 2. So this is gonna be I2. Okay, and this is 1, 0, 0, 1. That's I2. Okay, and I want to take the determinant of that and set it equal to 0. Okay. So what I'm gonna do is I'm gonna just distribute a negative lambda to each of these elements, okay, of I2. Okay, and so I'm going to get -2, 5, 6, -1. Plus negative lambda, 0, 0, and negative lambda. Okay, and then the determinant of that, when is that equal to 0? Okay, so we've got, this is -2 minus lambda. 5 plus 0 is 5. 6 plus 0 is 6. And -1 minus lambda. So let's take the determinant of that guy and set it equal to 0. So I'm going to get -2 minus lambda times -1 minus lambda minus 6 times 5 is equal to 0. So this is P lambda, but basically that's the characteristic polynomial. And if I set it equal to 0, it's called the characteristic equation. Okay, so let me distribute this and we'll solve for lambda. So I'm going to get 2 plus 2 lambda plus 1 lambda plus lambda squared minus 30 is equal to 0. Okay. So this is going to become lambda squared plus 3 lambda minus 28 is equal to 0. That's going to factor into lambda plus 7 times lambda minus 4 is equal to 0. And so I get lambda 1 equaling -7. And lambda 2 is equal to 4. So there's my eigenvalues. Boom. Okay, so those are the eigenvalues. Now, how am I going to find the eigenvectors? Okay, well, to find the eigenvectors, we're going to use the eigenvalues that we found and solve for the eigenvectors. Okay, so I want V1, and I'm going to let V1 equal to A1, A2. Okay. Okay, so remember our characteristics, our equation that we want to work with to find our eigenvectors is AV is equal to lambda V. Okay. Lambda V. Okay, so what was A? A was my matrix, -5, sorry, -2, 5. 2, 5. Okay, and then 6, -1. Okay. Okay. Times A1, A2 is equal to lambda times A1, A2. Okay. Okay, but what's lambda for V1? That's just lambda 1. Let's call this lambda 1. Okay, for eigenvector 1, we'll have eigenvalue 1, lambda 1. Okay, so -2, 5, 6, -1 times A1, A2 is going to equal what's lambda 1? It's -7 times A1, A2. Okay. Okay, so this is -2. Okay, -2 times A1 plus 5A2 is equal to -7 A1. Okay. Interesting. Okay, that's my first equation. My second equation is going to be 6A1 minus A2 is equal to negative 7A2. Okay. Okay, so now, well, I just get, if I add 7 over here, or add 7 over here, oops, not that, not that, add 7 here. Okay, this guy becomes 5A1 plus 5A2 is equal to 0. Which tells me that A1 plus A2 equals to 0, which then tells me that A1 is equal to negative A2. So they have to be opposites. Okay, that's interesting. The next equation tells me that 6A1 plus 6A2 also equals 0. Okay. Okay, so it's looking like these guys are linearly dependent, right? So, because they're basically the same. Okay, one equation I can multiply to get the other equation. Okay, and so if we were to kind of put this as an augmented matrix, okay, I would get 5, 5, 0, 6, 6, 0, and in one step, okay, if I did uh, a 1, 2 of negative 5, 6, or negative 6/5, okay, I would end up with 5, 5, 0 and 0, 0, 0. Boom. Okay, I could then multiply by 1/5, and I would get 1, 1, 0, 0, 0, 0. Okay, so I don't get a unique solution here. Okay, what I get is I get A1 equal to negative A2. Okay, and so if I let A1 equal R, say R, okay, then A2 would be, or let's let A1 be negative R, or let's let A2 be R. A2 equals R, then A1 is equal to negative R. Okay, and so, okay, then the vector V1, okay, the eigenvector V1 is going to equal to, I'm sorry, it's going to be an element of R2. Okay, such that, okay, V is equal to negative R times R, negative R, such that R is an element of R1. Okay. I'll just make that my solution set. Okay, let's factor out the R. So V is equal to R times negative 1, 1. Okay. Okay, so I could have any multiple of this. However, you know, if we just let R be 0, or let R equal 1, I only need one eigenvalue or eigenvector for that eigenvalue. So I only need one. So let's just let R equal 1. So I can say V1 is going to be equal to negative 1, 1. Okay. This eigenvector, okay, the eigenvector corresponding to lambda 1 equal negative 7 is negative 1, 1. Okay, so that's the eigenvector and eigenvalue for that one. Let's do the next one here. Okay, the next one I might do a little bit differently. There's a couple different methods that you could do here. The next one I'm going to look at this. What if we just wrote it as a v2 minus lambda v2 is equal to 0, and then we kind of, you know, said, well, I can only do this if I get a minus lambda I times v2 is equal to 0, right? Does this make the process any faster? Okay, well, let's let v2 equal, instead of a's, let's use b's in this case. B1, B2. Okay, let's let V2, okay, be B1, B2. Okay, and so we'll say A minus lambda I, okay, times B1, this is going to be a 2 by 2, times B1, B2 is going to equal 0, 0, 0. Okay, so we kind of like can do the subtraction and setting it equal to 0 all in one step. So it makes it a little bit faster. Okay, and so what was a minus lambda I? Well, that was just from up above. Okay, it was right here. Okay, a minus lambda I equals 0 is actually right here. Okay, so we already have that done above, so let's just use it. Okay, and then we'll solve. Okay. So that guy was negative 2. Yep. We just kind of subtract lambdas along the diagonal. So negative 2 minus lambda, we had 5, 6, and negative 1 minus lambda. Okay, we want that times b1, b2 is equal to 0, 0. Okay. So what's the lambda that we're going to use? In this case, we're looking for lambda 2. Okay, we're going to use lambda 2, which we found to be 4. So if we plug in our values, negative 2 minus 4, 5, 6, and negative 1 minus 4. Okay, b1, b2. Okay, I get negative 6, 5, 6, and negative 5. Okay. Okay, times b1, b2 is equal to 0, 0. Okay. And so I can do augmented matrix again. Negative 6, 5, 6, negative 5. Okay, and then augment that. And if we just add the two rows together, we can see that we can cancel out the second row here. So I would go A1, 2, 1. And I would end up with negative 6, 5, 0, 0, 0, 0. Okay. My augmented matrix. So what's my solution? My solution is -6 times B1 plus 5 times B2 is equal to 0. Okay, okay. That's good. Okay, so now let's solve for B2. Okay, in terms of B1, or maybe we'll solve for B1. Let's solve for, yeah, let's solve for B. Yeah, let's solve for B2. No, B1, sorry. Okay, if I toss this guy over here, I get 5B2 is equal to 6B1. Okay. It really doesn't matter what you solve for, B1 or B2. It's all good. I just wanted these eigenvectors to correspond back to our original problem. So I'm going to divide by 6, both sides. I'm going to solve for B1. Okay, so I get B1 to be equal to 5, 6, B2. Okay. But what if I let B2 equal 6R then? Okay, or in this case, since we used R's on the last eigenvalue, let's use S's here. Okay, 6x. Well, that would mean that B1 would be equal to 5, 6 times 6s, and B1, the 6's would cancel, that's why I use 6 here, and I would get 5s. So B1 is 5s and B2 is 6x. So I get 5s and 6s, okay? So V2, eigenvector 2 that corresponded to lambda of 4, okay, so lambda 2 equaled 4 there. Maybe I'll put that to the side, actually. And so V2 is equal to, or is an element of R2 such that V equals 5s6x, 5s6s, where S is an element of R. And so we have, okay, we could go to the next line. V2 is an element of R2 such that V2 is equal to, let's factor out the S, 5, 6. S is an element of R, okay. And once again, we'll just let, we need one vector to correspond to the eigenvalue, so let S equal 1, and so we get V2 equaling 5, 6. Okay. So our eigenvalue, or our eigenvector, corresponding, let me write this out as a sentence. The eigenvector corresponding to lambda 2 equals 4 is a V2 5, 6. Okay. How did I write it before? Yeah, that's fine. Okay, it's 5, 6. So to sum this up, okay. Okay, eigenvectors were lambda 1, lambda 2, equaling -7 and -4, or +4. Okay, and the corresponding eigenvectors v1, v2 equaled -1, 1 and 5, 6. Okay. So we've got eigenvalues and the corresponding eigenvectors. Okay. Yeah, good stuff. Okay, let's do one more of these. But we're gonna see what happens when we get our corresponding equation. Okay, to give us our characteristic equation to give us imaginary values. What happens when we have imaginary values here? Okay, number 3. Find all eigenvalues and eigenvectors of A equals 9, 37, -1, -3. Okay. Okay, so the first thing I'm gonna do is do A minus, I want to find the determinant of A minus lambda I is equal to 0. That will give me my eigenvalues. Okay, so this is going to be 9, -1, 37, -3. Okay, minus negative lambda 0, or sorry, I should say plus negative lambda 0, 0, negative lambda. Okay. So I want the determinant of that equals 0. Okay, and so this is going to be 9 minus lambda. Eventually, okay. I know that I'm just going to subtract lambda along the diagonals. Okay, so if I just subtract lambda along this diagonal here, okay, I'm going to get A minus lambda I. So minus lambda, this is going to be 37 plus 0 is 37. This is -1, and this is -3 minus lambda. Okay, I want to find the determinant of this. 0. Okay, so we're going to get 9 minus lambda times -3 minus lambda minus -1 times 37 is equal to 0. Okay, multiply out, we get -27 minus 9 lambda plus 3 lambda plus lambda squared plus 37 is equal to 0. Okay, so this becomes lambda squared minus 6 lambda plus 10 is equal to 0. Okay, this doesn't factor, so let's just use quadratic formula on this. Okay, so sorry. Lambda equals plus or minus, or sorry, -6, negative of a -6, which is +6. So negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, so this is going to be equal to 6 plus or minus the square root of 36 minus 40. all over 2. So this is going to be 3 plus or minus the square root of negative 4 over 2 is equal to 3 plus or minus, this is 2I over 2. And so we get 3 plus or minus I equals 3 plus or minus I. And if we get complex conjugates as lambda, they're always going to come in pairs. Okay, so lambda 1 is going to be 3 plus I, and lambda 2 is 3 minus I. So those are my eigenvalues. Okay, so eigenvalues. Okay, so now I just need my corresponding eigenvectors. Okay. So for lambda 1, okay, I'm going to get, okay, what was my original A? It was 9 minus lambda, 37, negative 1, and negative 3 minus lambda. Okay. So 9 minus lambda, 37, negative 1, and negative 3 minus lambda. I want to find out, multiply that times A1, A2. And that's going to give me 0, 0. Right? Well, for lambda 1, that's 3 plus I. So I have to subtract 3 plus I. So I've got to subtract 3 plus I from my diagonals. So this is 9 minus 3 plus I, 37, negative 1, and then negative 3 minus 3 plus I. Times A1, A2 is equal to 0, 0. Okay. And so I can simplify the top here if I distribute the negative. Okay, I get 6 minus I, 37, negative 1, and negative 6 minus I. Okay, times A1, A2 equals 0, 0. Okay, so now let's multiply this out. This is 6 minus I, A1. Whoops. 6 minus I, A1 plus 37, A2 is equal to 0. Okay. And negative 1, A1 plus negative 6 minus I, A2 is equal to 0. Let's gonna erase that. Okay, let's put this in an augmented matrix and try to solve for A1, A2. So we get 6 minus I, 37, negative 1, negative 6 minus I, 0, 0. Okay. Let's see what we can do here. Well, I could, if I multiply the bottom by 6 minus I, yep, by 6 minus I, if I multiply the bottom by 6 through by 6 minus I, then what do I get? Well, I get 6 minus I, 37, negative 6 plus I, it's nice. Okay, and then negative 36 minus 6I plus 6I and then plus I squared. Okay, that's cool. And then again, that's augmented matrix with 0, 0. Augmented with 0, 0. Okay. And then this is going to be equal to 6 minus I, negative 6 plus I, 37. The 6I and the negative 6I are going to cancel. The negative I, that's negative 1. So I would just end up with negative 1 time, plus negative 36, which is negative 37. That's cool. 0, 0. And so if I were to add row 1 and row 2 together, I would actually get 6 minus I 37, 0, 0, 0, 0. Okay. And so this tells me that 6 minus I times A1 plus 37 A2 is equal to 0. Okay, let's solve for A2. So if I toss that over there, I get A2 is equal to negative 6 minus I, parentheses, A1 over 37. Okay. And so let's let A1 equal 37R. Okay, so then what do we get? Maybe I'll let A1 be the negative, because then the negative will cancel out too. I don't have to worry about that negative. Okay, so then what's A2? A2 would just be 6 minus IR. Okay, because the negative would cancel out and the 37 would cancel out. Okay, so this tells me that A1 is negative 37R and A2 is 6 minus I times R. Okay, if I factor out the R, I get negative 37 and 6 minus I. And so my eigenvector that correspond to lambda 1, remember lambda 1 was equal to 3 plus I. Okay, then the corresponding eigenvector, okay, would V1, which is equal to negative 37 and 6 minus I. Okay, so that's lambda 1 and V vector 1. So eigenvalue 1 and eigenvector 1. Okay, cool, cool, cool. Now let's just do eigenvalue 2, which is 3 minus I. Okay, so that's going to be 9 minus lambda, which is 3 minus I. I would get negative 1, 37, and negative 3 minus 3 minus I. Okay, and let's do B1, B2 this time. Okay, for lambda 2, and that's equal to 0, 0. Okay, so this is going to be 6 plus I this time. Okay, so this is 6 plus I, negative 1, 37, and this is negative 6 plus I. Okay. Let's create the augmented matrix. So let's augment that with 0, 0. This allows me to erase. Come on. There we go. Okay, augment that with 0, 0. Okay, and then I'm gonna do 6 plus I this time, because I get a -1, that's gonna cancel out. So if I distribute that here and distribute that there, I'll get 6 plus I, okay, 37, -6 plus I, and then let's distribute this out. This is -36, okay, plus 6I minus 6I, plus I squared again, okay, 0, 0, okay. And so if I were to combine this, 6 plus I, -6 plus I, and then we get positive 37. This is going to become -37, just kind of like what we had before. And when I add these two together, I get a row of zeros. So they were, linearly dependent. So I get 6 plus I, 37, 0, 0, 0, 0. And so that tells me that I'm going to get 6 plus I times B1 plus 37 times B2 is equal to 0. Let's solve for B2. So this is going to become B2 okay, is equal to -6 plus I B1 over 37. So again, if I let B1 equal -37 S this time, right? Then if I plug that in, then B2 would be equal to 6 plus I S. And so B2. So I would get -37 S and then 6 plus I S. And if I factor out the S, we get -37 and 6 plus I. Okay, so for lambda 2 equaling 3, should be 3 minus I, right? Let's see what we got here. What was lambda 2? Come back. Okay. Lambda 2 equaling 3. Is it minus I? I think it's 3 minus I. Yeah, it's 3 minus I. Lambda 2 is 3 minus I. 3 minus I. And for 3 minus I, lambda 2, the eigenvector is -37 and 6 plus I. Okay, just so to sum up, we ended up with lambda 1, lambda 2, and eigenvector 1, eigenvector 2. Lambda 1 was 3 plus I, and we get eigenvector -37, 6 minus I, and for lambda 2, we get 3 minus I, and eigenvector 2 of -37, 6 plus I. Okay. Okay. And yeah, let's stop there. So that's 7.1.